Hello friends, welcome to lecture number 28. In today's class, we will read about a device called potentiometer. We will try to understand what all things can be measured through it and what is the basic principle or the working principle of potentiometer. Okay, so without wasting much of the time, let's go over to potentiometer. Okay, first of all, what it can measure, let us first know that. So we can write it is a device which can measure the following things. The first thing what it can measure is your EMF of a cell. EMF of a cell can be measured by potentiometer. Second one, what it can measure? It can measure the internal resistance of a cell. Okay, third thing which it can measure is it can compare two EMFs. Okay, that is E1 is to E2, it can measure, right? Then comes how it is constructed, how this potentiometer is being constructed. So let us come to the construction part. Okay, so basically it consists of a 7 to 8 meter wire. So it contains it is a 7 to 8 meter wire of a metallic alloy, of a metallic alloy, right? And the example of a metallic alloy is either your manganese or constantine. Okay, so these are the few examples of metallic alloys, right? Now why do we choose these metallic alloys? We choose these metallic alloys because here the alpha is, for metallic alloys, the alpha is positive and it is very less also. So what is alpha? Alpha is your temperature coefficient of resistance. Temperature coefficient of resistance. Okay, so for this reason we choose metallic alloys. Okay, now how it is constructed of? It is constructed of a board like this, which you can see, where it is fixed with a 1 meter scale. Here the way I have told you, it is in the meter bridge we have a 1 meter scale. Here also 1 meter scale is there. These are your binding screws. These are your binding screws, and that 7 to 8 meter wire is being rotated in this manner. This is the wire. Okay, it's being rotated in a platform, each of length 1 meter. Okay, now what are these? These are your brass connectors. Okay, they are connected because there will be less resistance or no resistance being offered to the wire. Okay, so all the wires which are connected in this fashion, they are in series. Okay, so this is the basic construction. Now your potentiometer is basically having two circuits. First one is a primary, the other one is secondary. So let us see what a primary circuit is. Primary circuit looks like this, which is having a cell whose EMF is ES, and we have a rheostat. Rheostat is a variable resistance. Then your ammeter, key, and AB is your potentiometer wire. So basically your AB is your potentiometer wire. And what all properties you know of this particular wire? The wire's length we know, the area of cross section also we know, resistivity we know, and resistance of this wire also we know. So all these four parameters of this potentiometer wire, which is AB, we know it. Then comes what is ES. ES is called as your driver cell. This is a driver cell, or which drives the primary circuit, or it is also called as auxiliary cell. Driver cell or auxiliary cell. Then what is RH? RH is your rheostat. RH is your rheostat, which is your variable resistance. Okay. Now let us calculate what is the current in the wire. We'll calculate current in the wire. Which wire? In the potentiometer wire, that is AB. Okay, so current will be how much? I will be EMF divided by total resistance. Okay, now here we have two resistances, resistance of the rheostat as well as resistance of the wire, and they are connected in series. So total resistance will be R plus RH. Okay, and what is the EMF here? ES. So this is the current which is flowing in the wire AB. Now what is VAB? VAB is basically your potential difference across the wire. Potential difference across the wire. Okay. So let me assume that this side is having a side A is having a higher potential, this is having a lower potential. So if I have in higher potential and lower potential. Okay. Now the potential difference across the wire will be how much? It will be current into the resistance. So what is the current flowing through the wire? We have just now calculated. It is ES R plus RH into R. So this is the potential difference across the wire. Now what is known to us? We know two things. Two parameters are known to us, V and L. We know these two parameters. Okay. Now the potential, V is the potential. So potential per unit length, potential per unit length, what it is? It is V by L. We know V, we know L also. So potential per unit length is termed as your potential gradient. It is termed as potential gradient. Okay, and it is denoted by K. Okay, do not get confused with your dielectric constant. It is a potential gradient. And what is potential gradient? V by L. Now the important thing which is to be marked here, that what is the job of the primary circuit? The objective of the primary circuit was to establish a potential gradient across the wire. Okay, so basically for the primary circuit objective was to establish a potential gradient across the wire, which we have established. K is equal to V by L, and if you talk about its unit, potential gradient unit will be how much? Volt per centimeter. Okay, from this also we can find we can know the principle of potentiometer. So one mark question comes, very very important, whether it may be your practical exams or your theory exams in CBSE. One important thing comes, what is the principle of potentiometer? So I am writing principle of potentiometer. Okay, principle of potentiometer. Now this principle has got a, you have to understand this principle of potentiometer. So basically the principle of potentiometer is the potential difference between any part of the potentiometer where is proportional to its length. Okay, so in short we can say V is proportional to L is the basic principle of potentiometer. So I hope up to this much it is very clear that what is the objective of primary circuit and what is the principle of potentiometer. Then comes the secondary circuit. So why this is required and what is its importance? We'll understand that. For that, let me construct the primary and the secondary so that it will be easier for you to understand. I have got the cell, I have got a rheostat here, RH, and here we have an ammeter to measure the current, and we have a key here, and this is your point A and point B, and point A and B we have a potentiometer wire. Okay, A and B is your potentiometer wire. So this is what I have drawn the primary. Now to this I will attach the secondary. How is the secondary connected? This is the EMF of the cell, which we call it as the standard cell, which is a part of the secondary circuit. This standard cell is connected to the galvanometer, then it is connected to a jockey, and that jockey can slide over the potentiometer wire AB. Followed? So now which one is the secondary circuit here? So this portion is your secondary circuit. Okay, and what is this point J? Point J is the position of the jockey. Okay, position of the jockey. So I hope this is how you should attach your secondary with the primary. Okay, now when they are connected, this primary and the secondary, they are connected, you have to keep some things in your mind. Okay, so while connecting primary and secondary, you have to take care of two things, right? The first thing which you should take care is your ES, positive of ES must be connected to the positive of E. So this is having a EMF E. Curly, let me substitute. Okay, E. Follow. The second thing is your driver cell EMF ES must be greater than your standard cells EMF. Okay, so this E we will call as your standard cell. This is your standard cell. So EMF of the driver cell must be greater than the standard cell, or else it cannot drive the current in the circuit. Okay, now we can also derive another potential information from this equation of potential gradient. We already know that the potential gradient K is equal to V by L. Okay, V I can write I into R by L. R I can write I by L is there, R will be rho L by A. So this L gets cancelled out. So I have K is equal to I rho by A. So this is also one of the important equations which will be required. Okay, now we will dive deep into to understand what is the basic job of your secondary circuit. The secondary circuit, the EMF with the cell which is attached to the secondary circuit, its EMF we can calculate, its internal resistance also we can calculate. How can we do that? Let us see that. Okay, for that, now onwards I will not draw the primary circuit. I will simply draw the potentiometer wire, and I will attach the secondary circuit, and I'll see how it works. Okay, so I have got this potentiometer wire. This is your point A and point B. Primary circuit is attached, but I am not doing anything to it. Okay, and this is connected to the standard cells positive, I have told you. So this is the galvanometer, and we have the jockey here, J. Followed. Now this is the positive end. So it is quite obvious your jockey will be your negative end, right? And let this length be small l. This length is your small l. Okay. So what happens when you move jockey? When you move jockey J, okay, then what will happen? L also changes. If I take the J towards A, L value decreases. If I take it towards B, the L value increases. So what I can say is the potential between A and J will be how much? It will be K, that is the potential gradient, into the length. That will be the potential difference between A and J, right? So if I am going to increase, if L value increases, then what will happen to VAJ? The potential will also increase. So basically the point what I wanted to say here, the potentiometer wire now behaves like a variable cell. The potential AB, the potentiometer where AB now behaves like a variable cell. Okay, how it will behave like a variable cell? Because I go on changing the value of L, so that depends on V, so I got a variable cell. Now how can I reduce this diagram which I have shown here? How this diagram is reducing? Let us see here. Here again what I will do, I will take this your AB as your potentiometer wire, and it is connected to a standard cell, again galvanometer, and we have got a jockey here. So basically you can draw this one, okay, and an arrow like this. So what this symbol tells you? This symbol tells you that it's a variable cell. Okay, this EMF is E, right? Now to this particular circuit, let me apply my Kirchhoff's law. Okay, to the secondary circuit, I will apply Kirchhoff's law. When I apply Kirchhoff's law, then I have to decide in which direction I have to move. Let me move in this direction. So applying Kirchhoff's law, I am writing KL for that, to the secondary circuit, SC I am writing. So net EMF in the secondary circuit will be equal to how much? Your E minus, now this is a variable cell value is how much? KL we have just now found out here. This variable cell will be KL. So E minus KL. Okay, this is the net EMF in the secondary circuit. Now this the net EMF, the equation net EMF is equals to E minus KL. It has to be verified, and it has to be seen that we will get 4 different cases from this equation, and many information we can draw from it also. So let us go for case 1. In case 1, if J is kept on A. If J is kept on A, what will be the value of L? It is quite obvious, it will be 0. If L is 0, then what will be V? V will also go to 0. V, which is equal to KL, that will go to 0. Then this equation 1, give it as equation 1. Then equation 1 will boil down to net EMF will be how much? E only. Okay. Now suppose at this situation, the galvanometer which is attached, suppose it shows a deflection like this. It shows a deflection in this manner. Suppose this is the null deflection, the center position. From here, now the pointer is somewhere like this. Let us assume that it is in this direction. So this is the galvanometer position. Okay, from the center it is like this. Now in case 2, let us see. In case 2, what I will do, J is moved towards B. Okay. So if J is moved towards B, what will be the value of L? It is quite obvious, it increases. If the value of L increases, what will be the value of KL? That will also increase. Then what will be my net EMF? It is increasing or decreasing? It is quite obvious that my net EMF will, since net EMF is E minus KL, so I will say that my net EMF will slowly go on decreasing. Okay, so the net EMF in the circuit will be increasing. Now what will be the galvanometer position? I have got this galvanometer here. This was the 0 position. Now it was seen that the deflection was something like this. So if I take this as theta 1, if I take it as theta 2, so it was seen that theta 1 is greater than theta 2. That means as I go on moving my jockey towards B, the deflection in the galvanometer is approaching towards the center position. Right? This is the case 2. Now what happens in case 3? Let us see. In case 3, a stage will come when your E is equals to KL. If I go on moving my jockey towards B, a stage will come when E is equal to KL. Then at that time, what is my net EMF? Net EMF in the circuit is 0. If my net EMF in the circuit is 0, then I can know that E is equal to KL, and at that particular time, the L is called as your balancing length. The L is called as your balancing length. Because this condition E is equal to KL, we will be using many a times when we will read in the next lecture about applications of potentiometer. Okay, so L is very important. How to determine L? That is very important. L is your balancing length. And this particular stage, this stage is called null deflection stage. Null deflection stage. Null deflection means the galvanometer will show no deflection at all. Suppose this is the galvanometer. Here this is the position for the center position O. Now you will see the pointer will be in this direction. I am giving it in red so that you can understand. The pointer will be somewhere here. Okay, no deflection will be shown. Now what about case 4? In case 4, if I still go beyond this balancing length, that means jockey J moves beyond the balancing length. I'll go still further towards the point B. That means your EMF will be less than KL. That means your net EMF is negative. If my net EMF is negative, then what will be the, where will be the pointer? I started with net EMF to be positive. It was towards the left. Now, if the net EMF becomes negative, you will find that the pointer of the galvanometer will move towards the right. If this is the center position, it will move towards the right. Okay, so this is actually one of the confirmatory test whether the connections you have done is correct or not. Take the jockey towards A. If it shows the deflection towards the left, then take the jockey to the point B, you will see the deflection has to show in the other direction, that is towards the right. If it doesn't show like that, then there might be two problems. What are the problems? The problem is either your ES is not greater than E, this condition is not satisfied, and the connection of ES and E, both which are the positive, they are not connected to the positive ends. So these might be the two problems. So you have to take care. So this is one of the ways by which you can check the connections which you have done is correct or not. So this is all about your basic principle and working of a potentiometer. Taking these concepts, we will apply it in the application of your potentiometer, where we need to compare the EMF of the cells, as well we will find out the internal resistance of a cell, okay, which I will do it in the next class. So I hope everybody must have liked this video. Please do not forget to share it, and please subscribe the channel, which is very, very important, which gives a motivation for me to go for further lectures like this. Okay, for any queries you can mail me in the mail ID which is given below. Thank you for your kind patience.